Guys, and welcome to part 8 of the book chapter summary. It's been quite a while, but let's get going. Today, we'll be going through SPI Flash. SPI stands for Serial Peripheral Interface and is a popular hardware-to-hardware communication protocol. We'll be examining on how to use it to create a persistent data storage in a flash memory. So, it uses 4 lines: the clock line, the MOSI, which stands for Master Out Slave In, MISO, Master In Slave Out, and Chip Select line. In general, the clock line is used to keep both peripherals in sync when reading data from each other. MOSI and MISO are the data lines, where Master Out Slave In means that the data is coming from the master device to the slave device, and vice versa for MISO. And Chip Select allows the master peripheral to select which hardware to communicate with. This diagram pretty much sums up the wiring of the Winbond to the STM32 blue pill. Now, the book uses Winbond W25Q32 or W25Q64 flash storage chips as its example. Flash storage chips are just basically memories which can be read, erased, and reprogrammed. It is non-volatile, which means that the memory persists even after power down. The general idea is this: we're going to send instructions to the Winbond flash storage chips through the SPI interface, telling it to read a block of memory or delete a block of memory. For those who are interested or curious, more information can be found in the datasheet, which I have linked down in the video description below. The book also mentioned that there is some issue with the CS line in the blue pill itself, in which it is not being pulled up. Thus, an external 10 km ohm pull-up resistor is required to use the SPI communication protocol effectively in the demo. Without further ado, let's take a closer look at the demo code given. The first thing you'll notice here is this command, which tells you to have a pull-up resistor on the chip select line. Otherwise, the SPI will not work. Then, if you scroll down right over here, you'll see a long list of defines. These are just basically bytecodes to perform specific instructions to the W25 flash storage chip. Then, as we look further downwards, notice that there are quite a lot of helper functions here that tells the flash storage chip what to do. They have this format where you first call the enable SPI API, where it causes the blue pill to pull down the chip select line and enable the clock line. And then the API SPI transfer is called to first send an instructional byte, followed by sending a dummy byte, and then this dummy API call will then return a value that is the result of the previous instruction. This value is then stored in a SRR1 variable, which is what ultimately the function returns. As we go down further, we will find the setup function and the SPI initialization codes. This function contains the GPIO setup for the SPI function. And if you look over here, there's this chunk of code which configures the SPI protocol, such as like the clock rate right over here. Let's go down even more. And finally, at the main function, we have this ATOS task. Let's go up to see what it does. This task basically functions as a serial terminal that takes in a USB serial input from the computer and then performs the instructions as required. So for example, when it detects the input E, it will instruct the flash chip to erase its memory. So that was quite a lot to take in, but that's just like the general idea. Now, let's jump into the demo to have a clearer view of what the code actually does. For the demo, I'll be using the Miniterm as the serial terminal. Once you have wired everything up, your serial terminal should show this menu interface that you can interact with. So first, let's check the flash status of the program device. I press S, or as you can see, it is being write protected. Let's write enable that by pressing W. Once you have done that, you can erase the entire memory inside the flash storage chip itself. To do this, you will press E, and then followed by pressing C to erase the entire chip. Right now, it's erasing the entire memory inside the flash storage chip itself. Alright, so once that's done, let's try to program some memory into the flash storage chips. Press A to go to the specific address. Let's go to the first address, which is the 0 address. So now that you're on the 0th address indicated here, right over here, as 0000, press P, to start programming memory into it. Let's say the very first few bytes we want it to be a bunch of zeros, right? So you need to do that. Just press 00000000. So this will indicate that the first 4 bytes of the memory address will all be zeros. Now, in order to program string memory into it, it's kind of tricky. What you need to do is put a quotation mark in front of every alphabet. So for example, hello world would be something like this. Quotation mark H, quotation mark E, quotation mark L, quotation mark L, quotation mark O, quotation mark W, quotation mark O, quotation mark R, quotation mark L, and finally quotation mark D. So press enter. Alright, so you can see here 14 bytes has been written. So in order to check what has been written, just press D. D is just a command for page dump. Page dump just basically gives you the first 100 bytes of the memory address. As you can see here, there are 4 zeros followed by the string literal hello world, which means that we have successfully programmed the flash storage chip itself. So that's it for the demo, and that will conclude this chapter summary. Hope you have a nice day and keep on learning. Thank you and goodbye.